Hello, I'm making a video on group actions because I'm procrastinating from studying for my finals. Oh, hi, Kat. So a group action arises when we have a group, say group G, acting on a set X. And let's suppose the cardinality of X is N. Then we define a homomorphism phi, which goes from G to Sn. This means that every element in G becomes a permutation in Sn, and it permutes all of the elements in X in some way. So for example, we can have an element G and suppose X equals to 1, 2, 3, labeled in whatever fashion. And then this G becomes a permutation. Say it equals to sigma. And since sigma is a permutation, it has 1 goes to some element, 2 goes to some element, 3 goes to some element. And as long as it's a bijective function, then it's valid. So for example, we can have 1 goes to 2, 2 goes to 3, and 3 goes to 1. Recall the definition of homomorphism. We have two properties we have to guarantee. The first one is that phi of 1, so phi of the identity in G, goes to the identity element in S of n. So phi of 1 permutes X in a way that doesn't change any element. So we can have 1 go to 1, 2 go to 2, 3 go to 3, etc. In other words, phi of 1 of any element X in X equals to X itself. The second property of homomorphism states that phi of G1, G2 equals to 5G1 and 5G2. Notice that the operation of G1 and G2 on the left-hand side is just the natural operation within the group G. However, on the right-hand side, since phi of G1 and phi of G2 are both permutations in Sn, the multiplication between them is a function composition. So for instance, if phi of G1 of X G2 of X equals to Y, and phi of G1 of Y equals to Z, then phi of G1 composite phi of G2 of X would be equal to Z. Hopefully that makes sense. For simplicity, to avoid confusion, I would like to write phi of G as phi of G subscript, just so that we don't confuse G as an element in X. So all of the subscripts are elements in G. Okay. Now that we have the homomorphism, we can define the group action. So we define a group action psi. It goes from G times X, the Cartesian product of the group and a set, to X. And here, phi of G and X, psi of G and X equals to phi subscript G X. So it's simply how the element G in the group G permutes a single element X in the set X. I hope there's a way to make sure that I'm writing the smaller element. So I'm gonna label the element as X bar so that you know it's an element in X, not the entire set of X. Okay. Now, group actions follow two group action axioms. The first one is that psi of 1x equal to X bar for all X bar in X. So the identity element won't permute any element in the set X in any way. This is intuitive since phi of 1 X bar equals to phi of 1 psi of 1 X bar equals to phi subscript 1 X bar. And from the properties of homomorphisms above, this would always equals to x bar. The second property is that psi of G1, G2, x bar equals to psi of G1 and then psi of G2 x bar. Similarly, writing this out as homomorphisms, we have psi of G1 phi G2 x equals to phi of G1 phi of G2 x bar. Here, this is just a function composition, so I can also write it as composite star. So it's clear that the group action axiom actually arises from the properties of homomorphisms that's defined at the very beginning of this video. So usually people use another notation to denote group actions instead of this whole chunk of things. Since we know that each element G in G is realized as a permutation in S of n, we know that we can write, say, psi of G x as G times x. And sometimes people write it as on G asterisk x, just for simplicity. For beginners, I would still suggest writing the function out explicitly, because then you wouldn't get confused on which element is in the group and which element is in the set.